So I've seen the first example, to understand this recursion pattern. Let me take one more example here to illustrate recursion slightly in little more, different way here. So the problem we are really picking out here is very standard problem. It's not so much useful in the practice, but very helpful to understand thought process of recursion. We call this problem as Towers of Hanoi. Let me state the problem, then let's see how do we really attack this problem by using up a recursion pattern. So the problem statement here, Towers of Hanoi. So what is the problem? The demanding here is we have 3 towers. We call this as tower A, tower B here, and also tower C. So on tower A here, we got n disks of different diameter here. All this, we call this as a disk innovation. So what should we really do? Find an efficient algorithm. Find an efficient algorithm that what they call recursive minimum number of moves required to transfer n disks from tower A to tower C. Instead of recursive, we call it as that displacive. So what do you mean by this? So tower A is available, tower B, tower C is available. Our job is here to move all these n disks here from tower A to tower C here. But how many minimum number of moves here required to transfer all these disks from A to C? You must display those moves. So ideally, if you look at this problem statement, there's nothing here. You got n disks here of each diameter. Pick up all of these disks here and just transfer to C. One move, we can actually able to transfer everything here. So there's no real challenge or fun, when you don't put restrictions on this problem here. That's why. So this problem is interesting if really place it up some restrictions now. So what are those restrictions here? So tower C, so subject to following conditions and everything. So the first condition is going to be you can only move here one disk at a time here. If I put this restriction only one disk at a time, you cannot take all 4. You take the first guy, now you can place on to C. Take second guy, place on to C here. Take a third guy, place on to C. Take a fourth guy, place on to C. So here also the problem is very straightforward to solve, because all we got to do here is take one after the other and transfer to C. That's what our goal. So that's why. So even this kind of variation, that the simple restriction is not enough here to really make this problem interesting. I'll put one more restriction, then this problem looks interesting here. The second restriction is going to be you cannot place larger disk on top of smaller disk. So let's see what do you mean by this. If I take this is in terms of diameter, we call it as larger and smaller. You take this top guy, which is smallest one, if you transfer to C, now you cannot take the second largest and or second smallest, I can say, you cannot place on top of it, because this restriction you have to satisfy. That's why. So now the only way we can really think of transferring n disks from A to C here will be exactly same way you have to transfer to C. The largest should be at the bottom, second largest on top of this, third largest on top of it, fourth largest on top of it. So that's what this problem is all about here. So given n disks here on tower A, your job is to transfer all of them from A to C by satisfying these two restrictions. And while doing that, so each disk move we call it as one transfer. That's what we really call it as how many moves required. So each transfer we call it as a move. So total minimum number of moves you got to really find it up here to transfer all the disks from A to C here. Then why they given B? Because if you don't have a B now, it's impossible to transfer from A to C here. That's why this we can call it as a helper tower or auxiliary tower here. That's why 3 towers make sensible to really to solve this problem in an interesting way here. All we have to do here is what is the most efficient algorithm to really solve them and for any number of disks and a issue. So that's what we really call it as Towers of Hanoi problem here. So how do you attack this problem? Like any problem, so first you got to understand the problem by taking bunch of examples here. They give insight into how to really can able to solve this problem here. That's why let me take a bunch of examples. So let's say n equal to 1. That means only one disk is given here. This is tower A, this is tower B here, this is tower C. This one disk, all you got to move here is to C, take it and place it onto C. We need just exactly one motion. There's nothing else we require. But when n equal to 2, then we got 2 disks here, disk 1 as well as disk 2. Now this is tower B, this is tower C here. What do we really want? Now, since we got 2, I cannot take off and place it onto C here. It's not going to work because we are allowed to move only one disk at a time here. And you cannot place larger disk on top of smaller. That's why if you take this, the second one, I call it as 1 and I call it as 2. Let me name this as 1. This is 1 and 2. So 2 if you keep on to C here, definitely there's nothing wrong with it. And you can bring 1 over here. Then again here, the smallest one you bring back to, the tower A. Then largest one you can keep on to the C. And finally the smallest one you can take it off. There's so many ways. Maybe let me write that. So first we are going to transfer, this is A to what do you call B. So the smallest one, or let me do A to C. A to C here. Then largest one, I'm moving from A to B. Then again smallest one you bring, because I need an empty space for largest one, C to A. Then the largest one is here, that is from B to C. Largest one is on C here. Smallest one, final move we are going to make here is from A to C. This is definitely a working solution where 5 moves we are making up. When I say A to C, always the top disk we are moving up. So we move this here and then we move this here, A to C. So the largest one is here. Since largest one should be on C, that's what our target enable here. The smallest one we are bringing back to the A. Now this is the empty tower. So then that's what C to A we have called up. Then B to C, the largest one is moving to C here. And final disk, which is 2, is moving back from what they call A to C. This requires 5 moves here. But is it the smallest number? Our goal is to find minimum number of moves. For one disk is available, minimum number is only 1. But when 2 disks are given, there are so many ways now out of them. How do you really know minimum number of moves required? So that's where, so let's look at from target point of view. So we don't know is it minimum number of moves or not. Let's make another attempt where, so what is our target here? I want to really take up the largest disk onto C. But I cannot take out the largest disk here because the disk 2 is on top of it. All you got to do here is take up this extra load which is available onto other tower. Then you can take this largest one and directly place onto C. But here it is going in indirect manner here. So first largest you go into tower B, then tower C here. It might really take a little more moves required so than minimum number here. We do not know. That's why let's try to attack to the target anyway here. Since target largest has to be onto C, your job has to be how to take off the remaining n-1 disks here to the auxiliary tower or helper tower so that largest disk can be taken to the C. So if I do that, so since only one disk is what they call an extra disk available, you keep on to the B. So my first move is going to be, instead of A to C, let me move to A to B. Now, so this is going to be here. That's what exactly here. Now my largest one, so free to move to C here. That's where the next move we are going to get here is A to C. So largest one is here. Once largest one is here, our remaining job is going to be take second largest, transfer to what they call C. That's what I call it as B to C. Now with these three moves now, these two disks were exactly able to bring to the tower C here. So let me write this as 3 moves in a vision. But is it the minimum here? So if this cannot be the minimum, what could be the other possible way here? But if you look at, in a contradiction way, so ultimately here, you have to bring the largest one here. If you want to bring to the largest one, the only way you can able to get a minimum here is take off the unnecessary disk, or which are overhead disks here, into the other tower. Only then I can able to get minimum. If try any other possible way, you cannot beat this three moves here. That's why. So in an intuition way, we can able to really conclude that without any mathematical proof. So logically, this 3 disks must be minimum number of moves here. That's why for n equal to 2, we really call it as what they call 3 moves are required as a minimum number here. But to get a more insight, to generalize for arbitrary n, let's increase this disks from 2 to 3. That's where I'm going to make it up. This is minimum number is 3. Let's take 3 disks here. Now tower A, tower B here, tower C here. Now we got A, we got B here, we got C. Now I'm taking a 3. So how do you transfer? The same thought process we have used for 3 will carry on here, where since my aim is to move largest one here, the only obstacle here is the top 2 disks here. Lift them off, keep in B, but that cannot be done with our restrictions here. That's why. So these two, if you can able to transfer to B first, then largest can be transferred to C. Then these two, again I can transfer back to C. That completes our complete movement here. But to take off these two, the top 2 to the B in a way here, we just solve the problem here. With 2 disks here, from any tower to any tower, what is the minimum, the approach to really get minimum number of moves here. That's why these top 2 disks here, you got to transfer from A to B. Let's take help of this idea. Let's do this work. So this top 2, now I call this as, 1, 2, 3. This 2, 3 if you want to move to B here. So this 2 and 3 if you want to move to B, what should we do here? So you have to really, since these two have to move to B, means this has to be on B first. The only obstacle is the top disk here. Let's take off this top disk here to C. That means we're trying to solve this 2 disk movement problem, which is an obstacle for largest disk innovation. That's where we're going to take it up here. First disk movement here is A to C. So once it goes to here, so this guy I can able to keep on to B. That I call it as A to B. Now once second guy is A to B here, this is a scenario now here. We got this disk and smallest is already here. Now we don't have these two anymore on the first tower. Now so C you bring back to B, C to B here. Now what we really can see here is exactly this. Now the top 2, which is obstacle here, is move to the tower B. The largest one now transfer to C. So let me write A to C. Now the scenario is going to be largest disk is on the tower C, which is target. Now our job is to take these 2 also to the C. But again, to take these 2, there is obstacle which is a smallest disk here. If you can able to take back to the A, then I'm free to take second largest to the C here. That's the next movement is going to be. So the smallest one you are going to bring back to the A. I call this as B to A. Then the situation is exactly like this now. Now B to C here. So which we are moving up. Then second largest is here. Now finally A to C, which is the smallest one, is here. So totally how many moves are required here? 3 plus 1 plus 3 here. 3 plus 1 plus 3, which is nothing but 7 here. So here 7 moves required for 3 disks here, and 3 for 2 disks here, 1 move for 1 disk. Now, so this is how you really get a working solution here, because Our job here is to generalize for n disks here. We do not know what is the approach. You take a bunch of very simpler examples to get an insight to really get working solution. So by taking this one here, there's nothing we can get insight, but n equal to, we really got a better alternative, which is 3 disks. The same approach if you continue here, the top 2, the minimum moves are required is here, and the largest one you kept back here to the target tower, and the remaining 2 again we transferred back to C. So 3 plus 1 plus 3, 7 moves are required here. So what's happening in this, what they call, whole process, if you observe, the problem is given to transfer n disks anyway here. So this stage, what we really have written here, so is nothing but, instead of moving n disks here, we are asking to move n minus 1. That means here we are asking here, so transfer only 2 disks here. So transfer 2 disks here. Transfer 2 disks from where to where here? A to B first. Then this is a straightforward thing from source to target, which is what A to C. I can write it as source to target. Directly we are able to move it up. Now what about this? Now if you see B to A, B to C, A to C here, we are moving 2 disks here, again from B to C. Here 2 disks from A to B, but while moving A to B, we are taking help of C and away here. So via, we can call it up C as a helper tower. But for the last 3 moves here, what are we doing here? Now again we are doing up a transfer, what do you call 2 disks here from, so B to C via, while moving B to C, I am taking help of tower A. So I'll take help of tower A. Then, so when we get complete solution and here. So problem is asking us to solve n disks to transfer, but we reduce this problem to smaller size, 2 disks here, one sub problem. And then after solving that sub problem, we know the straight move and away here. Again we are taking help of one more sub problem, which can help us to get the final answer and away here. So this is what essentially what we just defined as recursion. So solving a problem recursively means now you have to solve the problem by dividing this to smaller problem, again smaller problem, until you can solve it. Even these 2 disks here, we can know how to solve it. So here also the same 2 disk problem, instead of solving 2 directly, you transfer 1 disk here, then again target is moved up, this 1 disk you move to the top. That means even 2 disks I don't want to solve it. Again I can use recursion to reduce it further until you get a 1 disk here. When 1 disk is available, answer is very straightforward. You can move from the source to target. So when 3 is given, you have reduced the problem to what they call 2 disks now. You can take help of 2 disks again, reduce it for until you can able to get very small problem where you can know the solution straight away. But from that, you can able to solve n equal to 2. From n equal to 2, we can solve for n equal to 3. This is a solution building strategy. A recursive thinking means now 2 stages always will be there. One is the reduction of a problem. We don't want to solve for given n. You reduce the problem for large n to smaller and smaller until you get to the very small size where I know the answer. From that answer, you keep building up solutions to larger and larger sub-problems here. If you can, whenever you follow this, we technically label this as what they call recursive thinking. So one guaranteed working solution for this problem is going to be using recursion pattern. That's where. So all these things, let me really label this as solution 1. We call this as recursive thinking here. And reduction we can see, and also there are 2 sub problems, and this move is we can able to get once we can able to solve 1 sub problem. Before going to second sub problem, this move has to be performed here. So that's what for n equal to 3, how you can able to solve this problem. Let's generalize for n disks anyway here. Now if I give n disks in general, so let me write it out here. So I'm going to give in n disks now here. So 1, 2 here, and so on. The nth disk here, and this is tower B here. This is tower C here. A, B, C. So how are you going to transfer all these n disks from A to C? By taking this, what they call, smaller size examples, you can able to generalize it up here. And also you can easily prove this algorithm here. Any recursive thinking is very easy to prove it up. By using some base cases, you know their minimum number of moves. By using an induction tool, a tool of mathematical induction, by using that tool, we can able to prove that any recursive algorithm is going to work. We're not giving proof here, we are giving a logical reasoning here. But if you want to formally prove that, the tool from math for any recursive thinking is going to be induction. Base cases prove it, from the base cases try to prove that it is going to work for arbitrary n values. But let me generalize with our logical intuition. So where to transfer n disks from A to C, all you got to do here is first transfer. Let me write the steps here. So transfer. So n minus 1 disks here. N minus 1 disks from A to B first. This is first step. Then my largest one has to move. So obviously from source to target, one move has to be done, and followed by the n minus 1 has to be transferred from B to C. That's where, let me write here, transfer remaining n minus 1 disks here from B to C. So then we can get complete solution. So this is what our actual logic of what they call reduction, and how to really use sub problems to get final answer to the complete problem here. So let's really move on to the coding to see how you can transfer this thought into the specific practicality here. Once you can see in practice, so how this is can be implemented here, then we analyze the performance of the algorithm. Let's move on to the coding to see how to translate this thought into a particular language. So we have seen the idea of how to apply recursion to solve this Towers of Hanoi problem. How can you translate such recursive thinking into code? So here we got a folder or a project called recursive thinking here. Let me create a new class, which I call this as Hanoi problem here, or Towers of Hanoi. Towers of Hanoi. Now we keep the package structure as consistent lg.top20 basic here dot recursion main method to test this. Let's write what they call the prototype. So public static here void means we want to just a method. We are not using object programming, simple procedural style. So Hanoi of, now the arguments here, how many disks are available, what are those towers and here. Those towers I'm going to give as a single character literal. I can call this as src char aux here char target. End of this. This is the prototype. What is our first step here? Our n minus 1, which are overhead or obstacle for moving the largest disk, has to be transferred from source to the auxiliary first here auxiliary tower. So that we can express by using up Hanoi of n becomes n minus 1. To that n minus 1 is an obstacle. We are moving from where? SRC is SRC only. But our target now here I am going to use aux here. But the helper one we want to use here is going to be target. That's why I just have interchanged up those two arguments. So what is the meaning of this call is you solve n minus 1 disk transfer, disk movement here from source to the auxiliary, that is the target, by using our original target as a helper. So that is equivalent to this line of statement here. After doing the n minus 1 obstacle is free, then largest disk can move to the target. That is just a move, a display that, which is nothing but src plus, I'm giving a movement src plus, I'm going to give it as a string. So in a string I'm going to give a move plus here target. After finishing that, Then remaining n minus 1 which are in auxiliary tower has to be transferred to the target tower. That's where Hanoi of again n minus 1. So source now is going to be auxiliary, target is original target only, but our original SRC whatever is available is used as auxiliary here. That's why let me use SRC here. So target will be as is innovation. So there are the two recursive calls, and this process continues until we know when to solve this one. So we keep reducing until when one disk is available. Answer is very straightforward. Or you can start with 2 disks now, 3 moves you can write as a base case. There is no rules for the base case. You decide when size of the problem becomes what value you can directly solve the problem. That is all so your own decision only. I am going to choose n equal to 1 here. When n equal to 1, we know the answer, sys out, which is again SRC plus I am displaying up the move here to targets. Then after this we solve the problem, return back here. So this is how you can translate this so-called our recursive thinking into recursive code. But is it working out or not? Sure. Let me test this. Take a n value from command line here. Take integer dot parse here. Now with args 0 here, end of this. Now we got n value. I'm going to call Hanoi of n. What are the tower names? You can use strings, but I'm using characters here. That's where I'm giving a literal, b literal here, and also c literal here. So that's the conventions we are following up. So here Hanoi is actually displaying the mouse here. So let's execute this program here. So we need to pass what they call an exception, the value n value here. That's what the exception. Now go to the arguments. Let me give up 2 disks innovation. Apply, run. You can clearly see that A to B, A to C, B to C here. The smallest one you are moving to auxiliary. Now the largest one goes to C, from auxiliary to the target. 3 moves is what we have seen on the board. That's what is actually displaying. Let me run this for what they call run configurations. 3 disks here. Apply, run. We definitely get 7 moves here. 1, 2, again 3. So these 3 are actually to transfer from source to auxiliary anyway. Again the largest one you are moving to the target. Again the remaining 3 more moves. 3 plus 3 plus 1, 7 moves. That's again we have discussed. Like this, for any arbitrary value n here, we can able to get the moves anyway here. Let me take up one more value. For n equal 4, we expect 15 moves anyway here. Let's see whether we get 15 or not. So 1, 2, 3, 4, 5, 6, 7. The 7 moves to move the top 3 to the auxiliary. A to C is for the largest disk here. Remaining 7 here must be for 1, 2, 3, 4, 5, 6, 7 to move from auxiliary to the target. So this is how you can able to see in action the Towers of Hanoi thought into the code. But we do not know the performance of this algorithm here. Let's discuss theoretical performance of the algorithm. Then we can see in practice how this algorithm is going to perform. Let's move on to the discussion.